This is an update of some work that we presented last year at ShmooCon. And in particular, we have to tell you today about the results of a big search that we did, actually 3 different searches. So we'll go through the introductory stuff fairly quickly and then get to our results. I'm Mike. I started Great Scott Gadgets, and I make a lot of hardware and stuff.
And I'm Dominic, and I work for Mike, working on Ubertooth and various other little projects that are usually about communications technologies. Do we need this? No. Okay. If there's any doubt, I don't speak on behalf of the US government. Anyway, so we should outline the problem, which is we were sort of inspired by this whole LangSec movement, and also inspired by trying to defeat work that Travis Goodspeed had done, and that's kind of how we got to where we are now. And we pitched this as a DARPA cyber fast track program piece of research 2 years ago now, and essentially what we want to do is stop packets and packets from working. Now, I'm going to assume that most people in here have heard of the packets and packets attack. So, very briefly, you put an entire frame inside the payload, which you control from sort of user space on your system. You don't have access to a radio. You don't have access to SDR to do like horrible radio things. You control the high layer. So you put an entire valid frame inside the payload, and then you keep transmitting it until you get some noise at the receiver, and the incorrect packet gets received. And you can see this here in these packets down here that have been received. This is taken from Travis's talk. And he did this with Zigbee. But interestingly, Danielle and Andrea from Inverse Path managed to make this work with wired Ethernet, which was a fantastic Black Hat talk 2 years ago. And there's a paper on the Inverse Path website about it, and it's well worth a read. And they were able to do it, and the noise they had was someone plugging something into the switch, which just created enough noise to have frames mistaken. And theirs was a lot more complicated because of various mechanisms in Ethernet that are actually designed to stop this sort of thing, but clearly don't. And I guess in many ways this also relates to buffer overflows and anywhere where you're trying to separate different levels of privileged data. So you're saying we have data that's untrusted from the user, and we have data which the system is putting in, and things like that. And we want to separate them out in some way so that they're not mistaken for each other. And I'm aware this is vaguely solved by the no execute bit or anything like that, but it's also an application of our work. So what we define is ambiguous encapsulation, which is where you have data and you cannot, without context, without knowing anything about it, you cannot determine whether it's user-supplied data, whether it's code, whether it's metadata or something like that. And we're mostly interested in communications protocols, so you can't tell whether it's payload or header data in your packets. And unambiguous encapsulation is exactly the opposite, and that's what we're trying to define here, which is without the need for context, given a series of bits, you should be able to find a way to decode them and know whether or not they are privileged data or whether they are user-supplied data that you can't trust.
So we think of unambiguous encapsulation as being a general principle that can be applied in a whole bunch of different cases. Anytime you're encapsulating data within other data, we feel that it's good to encapsulate unambiguously, where there's no way and typically we do that by some means of encoding, so that say inner data are encoded in a completely different way than outer data are encoded. Therefore, you can't mistake one for the other. But we're particularly interested in as Dominic mentioned, communication systems. And in communication systems, if you keep digging down and down and down, sooner or later you get to the physical layer. And at that boundary between the physical layer and where you start having data, binary data, between there, you usually find some kind of an error control code. Either an error detecting code or an error correcting code, some kind of encoding that has some redundancy in it, as we learned early this morning, right? But that's an opportunity, actually, to take advantage of that layer of encoding. And we think that that's an opportunity to introduce a new type of encoding that encapsulates data unambiguously. So we're looking at error control codes, and in particular, we're looking at binary block codes. The reason we're looking at those is because they're simple, and we wanted to start with something simple. And we wanted to find out if we could investigate binary block codes and find binary block codes that we think are useful for the unambiguous encoding or the unambiguous encapsulation of data within other data, such as a payload within a frame. And so we're dealing with binary block codes that usually we specify having a certain number of data bits that are represented by that code, a certain number of bits in each code word, and a certain minimum distance. And we usually do, in this case, we're doing Hamming distance, which is the number of bits that are different between one code word and another. So just the classic example, the 743 Hamming code, it's every single code word. So you see that there's sort of a jumble of code words up there. There are 16 of them, which means that each code word can be thought to represent a data value between 0 and 15. So every single code word represents a 4-bit number, but it's encoded using 7 bits. And out of all the possible 7-bit codes, we only select these 16. And there's an analytic method to generate these things. And that's traditionally the way that codes are formed. But we're actually doing things a little bit differently. In this case, you get since there's a minimum Hamming distance, the number of bits that differ between any two code words is at least 3. So that means if one bit is flipped, you will not mistake it for another code word. You can correct that error. If 2 bits are flipped, you can detect an error, but you're not absolutely confident if you're receiving those bits or reading them. You're not confident which code word it was. And if there are 3 or more bits flipped, you could actually just completely receive the wrong code word and not know it. And that's entirely a function of the Hamming distance. So the greater the Hamming distance, the more immunity to errors there is. And what we're doing is showing when we're dealing with these codes, we're doing things in kind of a brute force way by implementing with a lookup table instead of implementing with a more sophisticated algorithm, which would be more traditional. And we kind of think of that as a brute force method. In the case of a small code like this one, a lookup table is a perfectly reasonable way to implement a decoder. And we can also take a brute force approach to actually generating the codes. So this big list here, all these different numbers, well, yeah, there's an analytic way to determine that set of code words. Out of all the possible 7-bit numbers, we choose these particular 16. Well, you could also find those just by doing a brute force search through all the possible 7-bit code words and find a set that meets the criteria that you're interested in. And that's a perfectly reasonable approach, we think, to finding a code, especially if you're going to implement the decoder with a lookup table anyway. So, jump back and show you our simplest example for a code that we think is useful for unambiguous encapsulation and why we think it's useful. Here's a code made up of 5-bit code words. There are 8 of them, so each one can represent a 3-bit number. And the minimum Hamming distance between any 2 of those codes is 2. Any 2 of those code words is 2. Now, if you were to take those 8 different code words and split them into 2 groups or 2 subcodes. Now you can see that the minimum Hamming distance within each subcode is 2, but the minimum Hamming distance between one subcode and the other subcode is 3. And we call these complementary codes, and we call this property of having a minimum distance from one subcode to the other subcode, we call that property isolation. And the idea is that there's a certain level of immunity to errors, where you could, if you have enough errors in comparison to your Hamming distance, then you might incorrectly decode something, but still think it's in the right subcode. It takes a higher threshold, a higher number of errors to actually break that isolation boundary and mistake a code word as being something that belongs to the other subcode. And we think that this is a property that might be useful for unambiguously encapsulating data, where maybe you'd use one set of code words for the header and the other set for the payload, for example, in a wireless communication protocol. So we call this particular type of code an isolated complementary binary block code. And in this case, if you look down at the bottom here, 1 bit flipped gives you a detectable error. 2 bits flipped gives you an undetectable error, but it is isolated. And you have to have at least 3 bits flipped in order to have something incorrectly decode as the other subcode.
So we wrote just a little C application. I think we wrote a Python version first, proof of concept. It was hideously slow, so we wrote a C version. And just to brute force the key space, and what it would do is you give it a set of input parameters, and it would go out and try and find the biggest code it could, so with the highest number of code words that fits your parameters. And the parameters you give it would be length of each code word, the Hamming distance, the minimum Hamming distance within those groups, and the minimum isolation between the two. And it will go out and try to find larger and larger groups. It just used a depth-first search recursive algorithm of the entire key space. It's just a big brute force. And we looked at other methods. Initially, we were planning to write some Verilog for and run the major search on FPGAs and buy some fairly expensive FPGA hardware. And we do have implementations of the various algorithms for this, but we weren't really sure that they were mature enough at the time, and we knew our C code worked, and we decided to go with cloud computing resources. So we went with EC2 instead, and we used a lot of computing power over the course of about 5 days on EC2. I'll come back to that in a second. The other thing is, after we gave a talk at ShmooCon in 2014, someone used the Z3 Python bindings, which is sort of constraint satisfaction solver, right? Mm-hmm. Yeah. And they were able to produce actually quite a fast method to prove that a code exists. But we stuck with our method because we wanted to find all the codes. So we want to know that we've done an exhaustive search, and part of the reason is that we want to find like the biggest code, and we keep looking for sort of larger and larger codes as we go. As I say, we ran this on EC2 and on like our laptops for various test runs and things, and there were some codes such as this 1579, so that's a 15-bit code, 7-bit Hamming distance within the groups, and a 9-bit isolation between the two. And it produced 111 gigabytes of output, filled up my hard drive, and then everything just fell over. So like there were certain ones, we started doing this with like various large sets in order to try and work out what we could reasonably expect to be worthwhile. And I think there's probably a hint there that if you get 111 gigs of output from this algorithm, that there are a lot of codes that exist there, and so you can probably alter your parameters to get actually like more efficiency out of it, i.e. you're probably wasting a lot of bits if there are a lot of opportunities for these codes to exist. I may not have said that very well, but yeah. Anyway, so that's also why we decided to only run for up to 8-bit codes for the main search, and then 1 to n for the Hamming distance, and the Hamming distance, the isolation always had to be greater than the Hamming distance. So yeah, we found like 19 million codes, and we have them all on a hard drive somewhere, and they would be publicly available if we had the bandwidth. But the algorithm's out there, and if you're interested in developing a communication method, you could go and you wanted to use unambiguous encapsulation, you could go and take a look on the code and generate yourself a code. And two things that were really quite interesting is we had a few codes, a few sets of input parameters that gave us similar subcode sizes. So you might want to use them if you've got, say, quite a balance between your metadata and your payload or anything like that, because you're going to be seeing a lot of both. Whereas we had one example where there's a subcode of 2 and the other one's got 44 codes in it. And if you've got a system whereby you actually have a very small amount of metadata and you want to encode far more bits in your data, something like that would be more appropriate because you can encode more values with the 44 than you could with, say, 4. Do you want to explain these?
Sure.
Yeah.
So we tried to identify different types of block codes that we thought had properties useful for unambiguous encapsulation. And one of the ones that we decided to look at was non-binary block codes. And so instead of a code word being a list of bits, a code word is a list of values that are not binary. In this case, we had values ranging from 0 to 6. We were envisioning what if we wanted to use it on some weird communications system like 7-level phase shift keying, which is a system that I've actually seen in real life. It's unusual to see systems like this that have a modulation that is an odd number or a number that is not a power of 2, but they do happen. And so we thought, well, we know we found these things for binary codes, but maybe let's try something that's non-binary, and 7 was just an example that we had. So one thing that we did differently here was we chose the Lee distance as our distance metric, where we used Hamming distance for the binary codes. And the Lee distance is simply the shortest number of hops from one point around the circle to the other. So the distance from 2 to 6, naively you might say that's 4, like 6 minus 2 is 4. But the shorter way around the circle, it's 3 hops. So the Lee distance, so it's a modular arithmetic subtraction, that's it. And it takes into account the cyclical nature of certain schemes like phase shift keying. So other than the fact that we changed the distance metric, it's basically the exact same concept. And so we were looking for, again, isolated complementary codes, just in this case, with a 7-level modulation instead of a 2-level modulation. And well, just to give you an example of one of the codes that we found, this first one here is made up of 2 subcodes. One of them has 2 code words, and the other subcode has 4 code words. So there's an asymmetric code like Dominic was talking about. And in this case, we had an isolation of 5, which is a whole lot of isolation for a short code word. And then we have a symmetric code example here at the bottom where we had code words that were 3 symbols long and had a minimum Lee distance of 5 and a minimum isolation of 7.
And again, we produced quite a lot of output. We tested about 11,000 different sets of parameters. And again, we just scripted it all and threw it onto EC2. And generally, we went up to 9. And I can't remember why we picked 9 rather than 8. I suppose it doesn't really matter. It wasn't binary. So we picked 9. So 20 gigs of what I would call successful output, because again, there were various runs that filled up hard disks and things like that. Poor planning on my part. But again, I don't think those results would be that relevant, because it implies that you're actually wasting a lot of capacity in your communication channel by the fact there are so many. I'm pretty sure that's true. But I'll have to go and get a piece of paper and work it out. So some processor is constrained by resources. I had a lot of conversations with an engineer on behalf of Amazon over the course of a week, trying to convince them that I wasn't. My EC2 account went from having one standard micro instance, which I just played around with once, to spinning up something like 650 cores in the window of 24 hours. And this is apparently unusual behavior to them. So, yeah, and we got about 19 million results for this. About similar number of results. Interesting. I may not have updated this slide correctly, because the value of n has changed, and that's the same number as the previous ones. We did get a large number, and it is very similar, which is why I missed it, I think, on this one. The bottom of this is correct. We got some really big asymmetric codes. So we have one with a subcode of 2 and a subcode of 10,264 code words. And that might, again, it's unlikely you're ever going to have a set of data that's so heavily weighted like that. But you might want to use those 2 other codes. You might not care about privilege of your data, but you might want to use those 2 other codes for starter frame and end of frame delimiters, which again would defeat packets in packets, because you couldn't spoof the starter frame or end of frame within your payload. And do you want to
So the third and final class of codes that we thought up that might be useful for unambiguous encapsulation was what we called large complementary binary block codes. And the idea is kind of born out of the fact that we're using brute force search to find these codes, as opposed to an analytic method to find these codes. And if you're doing brute force search, you notice that some of the rules that are generally followed for block codes could be ignored. Like, for example, do you need to have a number of code words that is a power of 2? Traditionally, people are generating codes using analytic methods that produce usually a linear code, which is made up of a bunch of code words, and that total number of code words being used is a power of 2. And that's convenient for encoding binary data, of course, because then every code word is a integer number of bits. It represents an integer number of bits. So, but we were finding things like this code, a code word that a code that has a subcode with 10,264 code words, not a power of 2. Traditionally, you might think, well, I'm just going to take the highest power of 2 that I can and only use 8,000 out of those 10,000 code words, and just skip the rest, ignore them. But you might have some use for having a non-binary number of code words. Another example might be that bottom one, 2 code words and 4 code words. Well, as a whole, that's 6 code words. And traditionally, you might not choose a non-power of 2 like 6, but if you can divide them into 2 and 4, then that could be very useful for encoding 2 different types of information. So if you do a brute force search and look for, forget about isolation, just look for a set of code words that has a certain n, the length of the code word in bits, and a certain d, the Hamming distance, minimum Hamming distance, and then just look for the largest sets of code words you can. Sometimes you find codes that have a power, like in this case, 20 code words meet this particular criterion. These of 8-bit code words with a minimum Hamming distance of 3, we found this set of 20 numbers, 20 of these 8-bit numbers that all have a minimum Hamming distance of 3, and we're just representing them in decimal form here. But 20, I mean, traditionally you might just throw out 4 of those and only use 16 and have each code word represent 4 bits. But you could take those extra 4 and use those, even though we don't have isolation, just kind of take advantage of those extra code words you get kind of for free.
Yeah, yeah. So again, the search space was, we did n is 2 to 15. They tend to be not as many of these, so we were able to do a much larger search, a much larger key space. We also, part of the reason for that is we're not looking for isolation, we're looking for a single subcode. So we didn't need to, there's not as much expansion of the parameters. And this is shown in the results because we only got a meg, and they all ended successfully. So this data is data we could upload if anyone was genuinely interested. I'm pretty sure I can find a web server that can hold that. Yeah, as I said, the search space is much smaller because you're not, you don't have that extra factor to it, that sort of extra branching factor of the isolation. And one of the things we mostly did was we only wanted the longest code for a set of input parameters because we're looking for those that are non-powers of 2 in length, preferably, because they're interesting to us. And if you find one of those, but then you find a power of 2 code that's longer, then really what you're doing is just not using all of a power of 2 code. So we were specifically interested in examples whereby the longest code that we could find was not a power of 2. And we found quite a few. Do you want to talk about this, or shall I talk? Yeah?
Well, another interesting note, even though we did find quite a few of those non-binary codes, for all the various parameters we tested, the majority had a largest code that was a power of 2, right? There were just certain cases, certain test cases where we found a large code that was larger than a power of 2, or larger than the largest power of 2 that we found, which was kind of interesting, but they do exist. So traditionally, codes are selected based on various properties, like the code rate or the efficiency and what the probability of having an error is and so forth. But we suggest maybe that people should select codes also based on looking for, considering what happens when encapsulation might break. In the future, we think some interesting things could be done with this, like we've talked about maybe trying to make a variant of 802.15.4 that uses unambiguous encapsulation and is not vulnerable to packet-in-packet. We think that probably the thing that we didn't explore, but I think is worth exploring with respect to error-correcting codes, is investigating the nature of noise or investigating the probability of different types of errors. Traditionally, and partly this is because codes are traditionally generated by analytic means, probability of error is really ignored other than having some sort of a distance metric, like a Hamming distance. And selecting codes based on their Hamming distance may not be as good as selecting codes based on a more thorough analysis of the probability of bit errors. And so you could apply a much more sophisticated metric than something like Hamming distance if you're doing brute force search compared to analytic methods. And that's something maybe not necessarily directly related to unambiguous encapsulation, but would be an interesting direction to go. And we do think that this is the general concept of unambiguous encapsulation is something that could find its way into file formats, could find its way into CPU architectures, could find its way into a lot of things that we haven't looked at yet. So anytime you encapsulate data within other data, we hope you'll consider unambiguous encapsulation. That's our sales pitch. Thank you to everyone here for having us. And do we have a little time for a question?
Then perhaps, again, a couple of questions. Follow it.
No.
Oh, yeah, okay.
Hey.
So following on from what you're saying about maybe not basing it on Hamming distance, could you think, as you see more and more low-power device with this nebulous Internet of Things, do you think you could use something similar rather than using Hamming distance, but to look for rotational errors due to clock skew? Is like you have a lot of low-power devices that might not have synchronization errors, so you might be able to look kind of one or two off to make kind of timing safe coding?
Yes, that is an excellent question, and actually something that we should have put on this slide, pointing out the fact that we didn't look at time shift errors at all. Not in any formal way anyway. I mean, we kind of talked about it a little bit, but we weren't searching for properties where, like, if you take a code word followed by another code word, but then you like shift a fractional code word number of bits into it, you might find that there's another code word there. And so that's a type of thing. If you were going to try to actually deploy or design a new protocol or a new file format or something where you actually wanted to use this property, that's a type of attack that you should probably look out for. And we haven't. So that's a really important point. But getting back to your question about there are intentional timing errors possible, and there are also unintentional timing errors possible. And unintentional timing errors are actually quite probable. And so that might be one of the things that you'd put into your probability model if you were trying to come up with a code generation method or code search method that took into account probability of errors instead of just a simple distance metric. I think that's an excellent point.
Further questions?
How much have you looked into whether there is any theoretical analysis of how many of these codes are there? Have you looked into this at all, or just focused on the brute force?
It's actually an interesting question, like the bounds of how many codes there exist in various for various criteria. And it's an area that there has been quite a bit of research on over the years, and it's not as well understood as I thought it would be going into this. Like, you can find papers that talk about, people have come up over the years with algorithms that tell us, or equations that tell us an upper bound on, or a lower bound on this like maximum number of codes that meet a certain criteria, set of criteria, and but nobody's come up with like a general way, even for fairly simple binary block codes. Nobody's come up with a general way to just like compute how many possible codes there are. It's really quite interesting, I think.
It's kind of surprising, but then again, knowing that there are hard problems in coding theory, maybe it's not so surprising. Do you have any idea, have you identified anything in what you've done where you might guess that it maybe is one of those hard problems from coding theory shining through somehow?
I'm not sure.
Okay. Yeah.
Thank you.
Yeah.
So,
We don't really have too much of a sense of how hard any of these problems is, but we do definitely believe that brute force search is a reasonable approach to take, but only up to a certain limit, right? Like, we're dealing with fairly short codes, fairly short code words, and in practical systems you might want longer code words, and in those cases it might make more sense if you wanted to just find a code to use that has longer code words. It might make more sense to use a constraint reasoning approach, but that's going to be an inexhaustive search, I think, And you might not have the best code, you just have a good one.
Yeah. As a former mathematician, I would say that combinatorics is really hard. And when you start digging, you'll never know what you're going to dig out. You know, you may get into algebraic topology, you may get into elliptic curves, you may get into any one of those areas quite surprisingly. So I'm not surprised at all that this is a combinatorial problem that's still hot. All right.
It should also be noted that brute force makes a lot of sense for the shorter codes, because this is something you need to do once when you design your system.
Yeah.
It's not a case that you need to do this as part of the process. So it's a one-off cost. Now, obviously, there are code lengths which just are not going to be feasible for this sort of thing. No one wants to wait 3 years for your piece of code to finish before they can publish their spec for the new communicator, Bluetooth 5 or whatever. But there are balances there and things. And so I don't think, while brute force isn't necessarily the most efficient method for doing this, it was exhaustive, which is what we wanted.
Nothing's wrong with brute force. But let me tell you, when I see that special character that's not confusable for the message character, that's the delimiter character, I will know how much it cost in EC2 cycles. I will respect that character. All right, let's thank the speakers again.